Okay, let's talk about mastering the four characteristic patterns for arrow pushing when writing reaction mechanism. There are really four characteristic patterns that you will use with any reactions that you're writing. Generally, it's some combination of the four, right? But if you understand the arrow pushing in these four patterns, then you'll be able to write mechanism for any reaction or come up with new mechanism for new reactions, right? So we're going to look at the patterns one by one. And I promise, if you get arrow pushing, you can master reactions in chemistry, whether it's organic one or organic two. It's important that you master arrow pushing. Okay, so let's remind let me remind you of what your arrow, the curved arrows actually indicate, right? So when you draw a curved arrow, you're not just drawing an arrow for drawing an arrow's sake, so to speak. It is precise, it's specific, and it has meaning. It needs to, the tail of your arrow needs to come from somewhere specific, right? And generally, the tail of your arrow shows where the electrons are coming from, right? Which is why we say it's drawn from your source. So the tail of your arrow is usually drawn from a lone pair or a bond because that's where your electrons are, right? You need to remember that. The tail of your arrow is generally drawn from a lone pair or from a bond, right? The head of your arrow, the curved arrow, must be placed so that it shows the formation of a bond or the formation of a lone pair. Okay, so please remember those things about the tail and about the head. I'll give you some more things that you need to remember when you draw that curved arrow. Okay, now let us look at rule number one. And any of the four can be rule number one. It doesn't really matter. Um, so one mechanistic pattern that is very common is making a new bond, covalent bond, between a nucleophile, between a nucleophile and an electrophile. Okay? Sometimes this is referred to as a nucleophilic attack. Let's talk about what a nucleophile is. So phile means like, nucleo is from the nucleus. So nucleophiles love the nucleus, right? So they love something positive. Remember in chemistry, it's an opposite attraction. So an electron will attract, electron is negative, so it will attract the nucleus because the nucleus is positive. So your nucleus loves, your nucleophile, I'm sorry, loves the nucleus, which means that your nucleophile is your source. It is rich in electrons. Because your nucleophile loves something positive. If in chemistry, if I love something positive, it means I'm full of electrons. Something positive is not looking for something positive, right? It's that positive negative reaction. Your electrophile, and it's use the words, it means electron loving, right? So if I am looking for electrons, I'm clearly not negative. If I'm negative, I'm not looking for more negativity. Hello? No. So your electrophile, right, loves electrons. So it means your electrophile is positive, which is why your electrophile is your sink. It lacks electrons, right? It's your sink. It is not the source of the electron. So when you look at a reaction, right, you're looking at a rich-poor relationship. The nucleophile is rich in electrons and it wants to give some to the electrophile, and the electrophile doesn't have enough, so of course it's willing to accept it, right? So it's that rich poor relationship. You're rich, give some to the poor. That's what the nucleophile electrophilic interaction is about. Okay? So I need you to remember what an electrophile is. I need you to remember what a nucleophile is. Let us look at a reaction. Let's talk our way through this. We're going to unpack a couple of things here. So remember, you're presented with a reaction, and this can apply to any reaction. You need to find your nucleophile, right? So you're going to find the nucleophile in the reaction, and you need to find the electrophile. Remember, the nucleophile is your source, right? So looking at these two things, I have the bromide anion, and I have a carbocation. This is a carbon with only 3 bonds to it. So it must have a positive charge. If you do not know why or don't remember, go back to the playlist that has fundamentals from general chemistry for organic. A carbon is only neutral when it has four bonds to it, right? That's a full octet, okay? Anything else, it has a charge. In this case, it only has 6 electrons, not 8. So it's lacking 2 electrons, which is why it has a positive charge here. Also, if you wanted, you could have calculated the formal charge. But use reasoning instead of calculating the formal charge, especially when you're doing reaction mechanism. The carbon does not have a full octet. It's lacking 2 electrons. Remember, electrons are negative. So if I lack 2 electrons, I'm going to be positive. So the carbon here is positive. Bromine is screaming over here with a big negative charge on it. This is your source. You could also see it's full of lone pairs. Okay? So your nucleophile in this reaction, and hence the source of your reaction of your electrons, that's your nucleophile, and this is the source of electrons, which means it's rich in electrons, right? This is my electrophile, which is my sink. Your sink is exactly what the word means in English. It's low in something, right? It's low in electrons. And of course, your carbon here with the positive charge is low in electrons because it can easily accept 2 to get a full octet. It has an empty 2p orbital. All right. Remember, when you draw your arrow, right, you draw your arrow with the tail starting at the source, right? When you draw your arrow must start from the source and proceed to the sink. So the tail starts at the source and moves to the sink. Okay? Remember, with your tail, the tail, which is what I told you at the beginning, the tail needs to go go from either a lone pair or a bond. In this case, it's a lone pair. So let us draw our arrow. The arrow will go from the source to the sink. So the tail will originate, and you have to draw it from the lone pair. You can't just draw it in mid-air. From the lone pair, right, source, and it goes to the sink, right? The sink is the carbon with the positive charge. So the head of the arrow ends right here. Now remember, wherever the head of your curved arrow is placed, it indicates either the formation of a bond, right? Or the formation of a lone pair. Write this down somewhere or put this on a sticky note. Whenever you draw an arrow from a lone pair to an atom, you're making a new covalent bond. Okay? So when I draw my arrow from this lone pair to this atom, what this is telling me is that the lone pairs here are no longer on bromine only. It's now in a bond, so it's been shared between the bromine and this particular carbon. So let's draw that. Also, remember this, right? Whenever you draw an arrow with your starting materials, it tells you what the product will look like. So whatever you do over here, the interpretation of this arrow must be shown on your product side. Okay? So let us draw what is happening here. So let me do this. rid of the arrow. And of course, there's no positive charge. So let's now talk about, so something I want you to remember. When you're drawing your product, right? Please put everything back. I did not lose this or this or this. So you draw that back, okay? What I now know is that my lone pairs here on bromine made a bond with this carbon. I'm going to highlight this carbon. I'm just going to make a blue dot. So this carbon right here, my bromine will make a bond with it. So this is what happens, right? Lone pairs here will make a bond with blue carbon. Let's draw that. Let's draw a lone pair making a bond on blue carbon. I need this bond to look better, right? Now, follow me. Here we have bromine, lone pair. Notice I still have these lone pairs. They didn't go anywhere. And the bromine needs to be bonded right here because remember, lone pairs, this arrow means that the lone pair here made a bond with the blue carbon, right? Bromine is still a part. Bromine is who these lone pairs belong to. So when you draw this bond, what it means is that the lone pairs are no longer just on bromine. They are being shared between blue carbon and bromine, which means you need to put bromine right here, right? Because this is your new bond. Let's give our new bond a new color. Let's give it a red. That's your new covalent bond, right? Your bromine still has these lone pairs because you didn't use them to do anything, so please put them back. Lone pair, lone pair, lone pair. Now, let's talk about the fact that your bromine does not have a charge. And you can calculate the formal charge, but I'm telling you, when you write mechanisms, reason it out. Okay? And in my first playlist, if you go back, where it talks about fundamentals for from Gen Chem for organic, you will see, right? I give you a list of atoms that you need to know when they are neutral, what they look like. Bromine, all your halogens are neutral when they have a single bond and three set of lone pairs, right? These 6 electrons. Outside of anything else, there's a charge, right? So if you notice here, it has a charge. It has a minus charge. So let's reason out why there's no charge here. These lone pairs here, so it has 2, 4, 6, 8. Over here it has 2, 4, 6. Still has 8, but notice what's happening to these electrons. These electrons, and I'm going to circle them, these 2 electrons are no longer sitting just on bromine. They're no longer sitting just on bromine. They're being shared between carbon and bromine in a bond. So do I have more negativity or less negativity? Less negativity because instead of having 2 electrons to myself, hello, I'm now sharing. So if I'm now sharing, that's less negativity. Hence, there is no charge on this bromine. Please remember your halogens. Any halogen, and I'm just going to use X to represent your halogen. Any halogen, it have a formal charge of 0 and it has a single bond and it's 3 sets of lone pairs, right? The 6 electrons. Once you see a halogen looking like this, there's no charge on it. Anything else, it has a charge, is a minus or positive, okay? So this is how your reaction mechanism go. Find your source, find your sink, you draw an arrow from your source to your sink, and don't forget where your arrows must originate from. And like I said, remember, if the arrow is going from lone pairs to an atom, it means where the arrow ends, the head of the arrow, you are making a bond between where the arrowhead is and where it's coming from. So you're making a bond between bromine and your blue carbon. Source, the sink. Remember where the arrow originates from. Remember where it ends. In this particular example, we only used one arrow, one curved arrow. There are examples where you can use more than one, and I want to use more than one to highlight. I want to use an example where you utilize more than one curved arrow to highlight some other rule that I had told you from the basics. If you haven't watched that video, that one is extremely important. It explains arrow pushing and you not overfilling valence. So let's look at another example. And in this example, we're going to utilize more than one curved arrow. All right. So the usual, we need to find our source and our sink. And if you practice reaction mechanism, it will start coming naturally. If you remember the little things I tell you about where the arrow originates and where the head ends, you will be able to write any reaction mechanism. You just need to find your source every time and just need to find your sink. And remember that when you draw your arrow, it means something. It is telling you what product you're making over here. Okay, so let's look at this example. Your source in this reaction, hence it's your nucleophile, is right here, right? Your sink is here, but which atom over here is your sink? It's the carbon right here, right? Now, let me remind you, just in case you have forgotten, this was also done in that first playlist with fundamentals from Gen Chem. Electronegativity between a carbon and a halogen, right? Because the halogen is way more electronegative, is way more, and I'm using X to represent the halogen, because the halogen is way more electronegative than the carbon. It hugs the electrons from this bond and pull them towards itself, inducing a partial negative charge. So if I'm pulling the electrons away from here towards X, right, I'm going to induce a slightly positive charge here, which is why this carbon, because it's bonded to chlorine, can act as your sink. It has a partial positive charge, okay? So this is your sink. This is my source. So we're going to do what we do best and draw curved arrows. We're going to draw a curved arrow. Remember, your curved arrow need to originate from lone pair or a bond. In this case, only your lone pair, right? That's our first arrow, okay? So we went from our lone pair to the sink, okay? So being able to identify your source and your sink is extremely important. And they tend to be, if you do enough reactions, they tend to be, you're looking out for the same thing. And every time you learn a reaction, by the way, you're taught where the source and the sink is. So if it's alkene reaction with water, you know your source, you know your sink. So if you memorize most of this is memorization also concept. Okay, let us look at what this arrow translates into. Okay, so I am going to move this arrow so I can draw down here. So let's look at what product we're getting here and let's talk about it. Let's go ahead and draw what our arrow is indicating. Put my oxygen back. Now, let's do this step by step. These lone pairs are still there. I didn't use them. Please put them back. It doesn't matter where you put them. You can put them above and below. Now I'm using these lone pairs right here. Remember, wherever the head of the arrow lands or ends up, it means you're making either a bond or you're forming a bond or a lone pair. And I told you from a lone pair to an atom, when the head ends on an atom, you're making a bond. So we're making a new bond between the oxygen, and this carbon right here, okay? So I'm going to number these carbons 1, 2. So we're making a bond between the oxygen and carbon number 2. Number 1 is clearly still there. So let's draw our new bond. This is my new bond, right? Let's draw my new bond. That's my new bond. I'm making it blue, right? So that right there is carbon number 2. Carbon 2 has carbon 1 on it, right? And it's also bonded to my Cl, right? Question for you. And if you have forgotten this, I need you to go back to line angle. Let's look at this carbon right here. Are there any hydrogens on this carbon? Yes, they are. There are 2 hydrogens here. One here, one here. Remember, in line angle, hydrogens are not shown. So I have a hydrogen here and a hydrogen here, right? So let's chill out. We made a bond between the lone pair here and this atom right here. Beautiful. That's our blue bond, okay? Nothing wrong with that. That's exactly what this arrow means. But we have a problem. Remember, you can't overfill your valence, right? So my little carbon here, and I'm going to make it purple up here. Well, you probably can't see that. Make it blue. Let's make this carbon blue, right? We have a problem, people. Listen, here is my carbon, right? I made the new bond, my blue bond, perfect. But look what's happening to your carbon. You now have 1, 2, 3, 4, 5 bonds. Remember, one of the rules for mechanism is you cannot overfill your valence. Carbon, it's going to have 4 bonds or less. You can underfill, but you can't overfill. Okay? And if you underfill your valence, then it has a charge. Here, this is abomination. You can't do this. Okay? Not allowed. Okay? You can't have 5 bonds. So this is what needs to happen. Somebody needs to be lost here. Okay? So this is what will happen, right? When you make the bond between the oxygen and the blue carbon, you also need to break the relationship between blue carbon and chlorine. And how is that done? And I need you to write this down somewhere. You draw an arrow. Remember, your arrow can originate from a lone pair or from a bond. In this example, it's being originated from a bond. When you originate lone pairs, when you originate your arrow from a bond onto an atom, right, it means you're breaking that bond. You need to write that down somewhere. When you draw an arrow from a bond onto an atom, you are breaking this bond. Because what you're doing, right? Remember, right now, this bond means that electrons are being shared between blue carbon and chlorine. When I do this, it means I'm putting the 2 electrons that's here onto chlorine only. So I'm breaking them up. Nobody is sharing anymore. The electrons from here are only going to be with chlorine. So I have broken up with blue carbon. So in essence, chlorine is stealing. Okay, chlorine is taking the 2 electrons that makes this bond and is taking it for itself. Okay, so it's done with this carbon. So when you draw this arrow, please remember, from a bond onto an atom, where the head of the arrow ends, you're putting lone pairs. Because remember, there's only 2 situations. Where the head of the arrow ends by an atom, you make a bond. If it ends on a, if you go from a bond, onto an atom, you're putting lone pairs. Originate from a lone pair to a atom, you're making a bond. Write that down. Originate from a bond to an atom, you're putting a lone pair on here. So this is what happens. Let us remove this before the other chemists in the world start screaming. Right? So we end up forming, right, chlorine. And remember, chlorine had 2, 4, 6 electrons, but I'm putting 2 more on it. So it now has 8, right? So it must have a minus charge, okay? Remember, chlorine here, of course, has no charge. I just explained to you that your halogens with a single bond and 3 lone pairs has no charge. But look, and you can think about it. I'm taking the electrons initially. The 2 electrons was being shared between chlorine and the blue carbon. That's what a bond means. It has 2 electrons that is being shared between these 2 atoms. This arrow came in and put the two electrons here onto chlorine, right? And I'm gonna make them red. Let's make them red. These are the two electrons that it came and put on to chlorine. So if I give chlorine two more electrons, of course it's gonna have a negative charge. So it has a negative charge, it's no longer neutral. Source to sink, you must look for that. Remember where the tail of your arrow originates from. Lone pair bond. Look when the head of wherever the head of your arrow ends up, right? It's either you're making a bond or it's forming a lone pair. And I gave you the two cases where it makes a bond and where it forms lone pair. If you remember those, any arrow that's drawn from anywhere, because sometimes you get questions where arrows are drawn and they ask you to draw the product from the arrows that are indicated. You can do that. You can just remember the two little things that I just told you. And the key again is practice, 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 practice. Okay? So this is just one rule. There are three more. If you know these four, you can write any reaction mechanism.